Hello, my name is James Wahlberg, and I'm here to talk to you about molar solubility. What we'll learn in this video is how to describe molar solubility, to talk about what it is, and then how to apply it, how to use it to compare the solubility of different salts. To do that, let's break this phrase molar solubility down into its two components. As you know, solubility is the ability of something to go into solution, or how soluble it is. I like to hear it as solubility. And just like with any other ability, like your ability to dance in ballet, let's say, the greater your ballet ability, the better you are at classical dance. The better your basketball ability, the better you are at playing basketball. So too, the greater the solubility, the more something is able to dissolve into solution. So none of that is news to you. What we're going to do here in this video is talk about how molar solubility lets us be very quantitative about that idea. Not just descriptive, but to actually put some useful numbers on it and a way to make comparisons numerically between different substrates. So to see how that works, let's start with a hypothetical example. Imagine, if you will, that we have a container of water. Let's say that this holds 1 liter of water. And let's say that we put some sugar in it. So there goes our sugar cube down to the bottom of the water. And I'm sure that you will not at all be surprised if we drop our sugar into that water and walk away, let's say for half hour, an hour, something like that. We'll come back and the sugar will be almost completely dissolved. Let's say that we put enough sugar in that solution so that there's still a little bit on the bottom, that the saturation level is such that this water is as full of sugar as it can be. Be that as it may, the sugar has done a great job at dissolving. Contrast then to what happens if you take a cube of stone and drop it into a liter of water. You can come back in half an hour, a day, a month, a decade, a millennium, and almost none of that stone will have dissolved. It will seem to be exactly the same condition as it is when you first dropped it in there. It just does not dissolve very good. Its solubility is very poor. So if you think like an Olympic judge, you could say that the sugar is awesome at dissolving. Let's give it a 10. It's an amazing dissolver. Likewise, if we give a score to the stone, it is a very poor dissolver. So let's give it a score of 1. Now, this is just an arbitrary numerical system from 10 being awesome down to 1 being not so good. What we want to do then is to get much more scientific and much more precise than this arbitrary scale. So to do that, let's focus on the second term in molar solubility, and that is the molar part. And as you know, when we talk about things in moles per liter, we're talking about molarity. And of course, a mole is 6.02 times 10 to the 23rd of whatever you're talking about golf balls or social media contacts or whatever. It's just a quantity, right? Just in the way that a dozen is a quantity. So you know all this. Then to apply it to molar solubility, let's go back to our two substances. Let's start with the one that dissolves very well. Let's imagine that we have a mole of this substance. And yes, this looks like a dozen eggs, meaning to apply that analogy of a quantity of a dozen or a mole. So let's say we put that mole, again, into a liter of water, go away for a while, and we come back and almost all of it has dissolved. In fact, if we get quantitative about it, we started out with 12 of these units of substance there, and only one of them is left. Therefore, 11/12 of a mole have gone into solution. So we could calculate the molarity of that solution. It would be 11/12 of a mole per liter if this were a liter of water. Now, going over to the less soluble substance, let's say again that we have a mole represented by this dozen of egg-like objects. And again, this is a very, very poor substance in terms of its ability to dissolve. So let's go away for a while, however long that may be. And let's say that some has dissolved. And quantitatively, you can see where we started with 12 particles. Now we only have 6. So there is 6/12, or half of a mole in solution. Well, comparing these two substances now, you can see that the much more soluble substance, the one on the left, has a higher concentration in solution when the solution is saturated. So we have 11/12 of a mole in this example in this saturated solution, but for the less soluble substance on the right, we only have 1/2 of a mole or 6/12 of a mole to make a saturated solution. That's as full as this solution can be. So that same idea that the substance that's really good at dissolving, the substance on the left, we now have some quantitation. So the idea is that we can use molar solubility as the concentration of solute in a saturated solution. And that's the key. What we're really doing is measuring at saturation, what is the concentration of the substance in solution. The higher that is, the more substance that's in solution, the more soluble the substance is. Okay, so let's take this to some actual applications. Here we have a couple of carbonates. And as I'm sure you remember from solubility rules, carbonates in general are very insoluble. And that's exactly what these numbers suggest. Look how tiny these molar solubilities are. We have 6.9 times 10 to the minus 5th for calcium carbonate and 3.9 times 10 to the minus 8th for lead carbonate. So both of these substances are just barely soluble. They hardly go into solution at all. Their molar solubility, both of them are very low. And yet, look at the difference between them. We have 3 orders of magnitude from 10 to the minus 5th down to 10 to the minus 8th. So 1,000-fold difference in solubility. Even at this very insoluble level, these very insoluble carbonates, still molar solubility lets us make a comparison. And as we saw a moment ago, the greater the molar solubility, the more soluble a compound is. Therefore, the calcium carbonate of this pair is the more soluble. Let's look at another. Here we have 2 hydroxide compounds. We have an iron hydroxide and a lead hydroxide. Now, the interesting thing about these compounds, of course, is that hydroxides often are very soluble. For example, sodium hydroxide. I'm sure you're all familiar with sodium hydroxide, a very strong base. It completely dissolves in water. So this might be a little bit of a surprise. What that really is telling us then is that this solubility, this very low solubility, must have something to do with the counterion, the iron and the lead. Perhaps there's something about them that makes them less able to associate with water, to become solvated and to go into solution. Be that as it may, we can make the same comparison. We simply have to compare the molar solubilities. So we're looking for the higher number. And again, we have very small values. We have negative exponents here. But with negative exponents, of course, the smaller number is the larger number. So therefore, about 10 times more soluble, almost, not quite 10 times more soluble, is the lead hydroxide compared to the iron hydroxide. Let's take a look at one last example. Here we have barium fluoride and calcium fluoride, and at first glance, the numbers are the same. So it might be tempting to say that these compounds have the same solubility. However, if you think about the basis for molar solubility, it is the concentration in a saturated solution in terms of moles per liter. Now, the barium fluoride here is in terms of moles per liter, but that calcium fluoride is in terms of, that's right, grams per liter. So we're going to have to change that into moles per liter so that we can make the direct comparison through molar solubility. Here we go. So here is the solubility, 1.6 times 10 to the minus 2 grams per liter. And to convert into moles per liter, we're going to use the molecular weight. But notice what we've done here. We've taken the molecular weight, 78.07 grams per mole, and we've in essence flipped it on its head. So we have 1 mole for every 78.07 grams. And the reason, of course, for that is so that we get the unit cancellation to come out the way that we want. So just a reminder to always pay attention to dimensional analysis as you set up equations in chemistry. And we know we've used that ratio correctly, that molecular weight ratio correctly, because our units cancel and we end up with moles per liter. So when we convert the calcium fluoride into molar solubility in terms of moles per liter, we see that it is 2 times 10 to the minus 4 moles per liter, which is less than the barium fluoride, 1.6 times 10 to the minus 2 moles per liter. Therefore, the barium fluoride is more soluble. All right, I hope this helps give you a good handle on molar solubility. Keep up the good work, and we'll see you when we talk about KSP and molar solubility in the next video.